Okay, folks, in this video, we're going to talk about ideal gas law, the third topic of chapter 10. Let's take a look at what ideal gas law is. Well, previously we talked about 4 sub-gas laws. Okay, let's just do a quick review. Well, in Boyle's law, we know that PV equals to a constant. Okay, and in Charlie's law, we know that V equals to a constant times T, temperature. And in Gay-Lussac's law, we know that P equals to a constant times temperature. Okay, and then last one, Avogadro's constant, Avogadro's law, we know that V equals to a constant times mole number. And if you take a look at the comprehensive view of those 4 gas laws and do further research, you'll realize that all of 4 of them can be summarized by just one equation, and that is PV equals to nRT. Why do I, here, of course, P equals to the pressure. The unit is 1 atm. V is the volume. The unit should be liter. N should be the mole number. R is a constant. So R equals to 0.08206 units, liter times atm, and mole times K. Okay, so actually this unit here tells us what unit we should use for P, V, and T, and also N. P is a pressure, we should use atm, atmospheric pressure, as a unit. V is a volume, we should use liter as a unit. N, of course, mole number. T is a temperature, and we should use Kelvin as a unit. All right, so this is R. This unit, this constant will be given in your test, but please make sure you are using the right units for the calculation. Okay, now let's go back to this equation. Why do I say that this is a comprehensive equation for those 4 gas laws? Well, let's just use Boyle's law as an example. Well, we say that Boyle's law, PV equals to a constant. That means as long as you keep the mole number and the temperature as a constant, then on this side it's going to be a constant. So that reflects what the Boyle's law is. All right. And how about the Charlie's law? V equals to a constant times T. Well, apparently if you reorganize this equation a little bit, that equals to V equals to nRT divided by P. Well, if you keep the pressure as a constant, N constant, R constant already. So these 3 items, they are constant. That will tell you that V equals to a constant times T. That's exactly what Charlie's law says. All right, if you check the other 2 laws, they can all be reflected by the ideal gas law. Okay, so this is the equation of ideal gas law. It reflects the mathematical connections among 4 items: pressure, volume, mole number, and temperature. Now let's use this example to demonstrate how we use ideal gas law to do calculation. Well, calculate the volume. All right, this is what we need to do. Find out the volume occupied by this many mole of oxygen at the pressure of this 0.675 atm, and the temperature is this. Well, let's just plug those data in this equation. Remember to use the right unit. So PV equals to nRT. P is 0.675 atm, 0.675 atm times volume. Volume is unknown, so V equals to nRT, N 0.325 mole R, we know it's 0.08206 liter ATM mole Kelvin. And then temperature T, of course, convert degrees Celsius to Kelvin, 35 degrees Celsius plus 273.15. All right, so this is the whole equation. Well, I would say that gas law is quite straightforward when you try to use it. Just pay attention to the units and pay attention to your calculation. All right, now if you do the calculation, I'll do one more step, ATM times still V equals to, if you do the calculation on this side, remember the unit here, mole, can be cancelled. Of course, this one, after you do the calculation inside the parentheses, the unit should be Kelvin, and Kelvin can be cancelled. Therefore, for this intermediate step, the unit's answer would be 282.2142 L times ATM. All right, so the volume equals to 8.2142 L ATM divided by 0.675 ATM. All right, ATM get cancelled. Therefore, the final answer should be 12.2 liter. This is the ideal gas law. Based on the ideal gas law, we can further derive the molar volume of a gas and also a density of a gas. Okay, we'll talk about the molar volume in this slide, and we'll talk about density in the next slide. Molar volume, what does that mean? How do we define molar volume? Here is the definition. The volume occupied by 1 mole of a substance, apparently here would be gas, at standard conditions. Standard conditions means temperature equals to 273.15 K. That means 0 degrees Celsius. And pressure should be 1.00 atm. All right, so how do we find it, the molar volume? Well, according to ideal gas law, PV equals to nRT. You can reorganize this equation. Okay, divide the P by two sides. That equals to V equals to nRT divided by P. And since at standard conditions, we know temperature, we know pressure, N, 1 mole, R, constant, so we can mathematically calculate how much the V is. So V equals to 1.00 mole times R is a constant, 0.08206 L ATM divided by mole times K. And don't forget about the temperature. Okay, temperature is 273.15 K. And at the bottom, the P here is 1.00 atm. All right, now if you do the calculation right here, result would be V equals to 22.4 liter. What does that mean to us? It means that no matter what gas molecule you are talking about, as long as you have 1 mole of the gas, temperature is this, pressure is 1 atm, the volume of the gas would always be 22.4 liter. And this picture shows us the ideal behind the molar volume. Well, you have 1 mole of the helium gas at standard temperature and pressure, standard conditions. 1 mole of xenon at standard conditions. 1 mole of methane at standard conditions. And you can see that all three of them have the same volume. So that's the molar volume. That's how we define it. Okay, so it's quite interesting to see that different gas will have the same volume when you talking about the standard conditions. All right, so this is molar volume. All right, now let's take a look at density. We know density, the gas, different gas will have different density. And this picture shows us, helium. You can use helium to inflate the balloon, and the balloon can float and fly around. And neon, if you have a neon balloon, you will realize that neon balloon a little bit heavier than helium if the balloon have the same size. And if you are talking about an argon balloon, krypton balloon, and xenon balloon, you will realize one by one they are getting heavier and heavier. And this is related to the density of those gas, noble gas molecules. All right, so based on the ideal gas law, actually, we can use math equation to reflect why we have this kind of trend. Let's start from the ideal gas law. We know this already, okay? PV equals to nRT. Based on the definition of density, we know that density is defined as mass over volume. Okay. Well, apparently that you have the volume involved in the ideal gas law. And how about mass? Well, mass is not directly related to the ideal gas law, but if you take a look at this, the mole number is related to the mass. Okay, so in other words, in order to find out the density of a gas, you need to reorganize this equation a little bit. Okay, so now based on the definition of the density, we know the volume is at the bottom of the division. Therefore, how about we divide the two sides by V? So that means P equals to nRT equals over V. All right. Now, we want to have mass on top, so we should keep the mole number on top. And that means that if we divide the two sides by R and T, then you will get this equation, P divided by R and T, that equals to N over V. All right, we are getting closer and closer to the desired density equation. Okay. All right, now what we need to do is remember when you have mole number, how do we define mole number? That equals to the mass divided by the formula weight. All right, so in other words, I can plug this equation into this side. That will tell us P over RT equals to mass divided by formula weight, and then you still have the volume at the bottom. Okay, now remember our target is to come up with the mass over volume, and you have a formula weight here. How do we reorganize the equation to make it disappear on this side? Well, what you need to do is multiply formula weight on two sides. Okay, so that will give us P, pressure, times the formula weight divided by RT equals to mass over volume. And we know that mass over volume is density. All right, finally, we got density of a gas equals to P times the formula weight over R and T. Okay. Now let's revisit this picture here. As we said that, helium, neon, argon, krypton, xenon, they are in the same group. And noble gas molecules. And when you go from top to bottom, it's getting heavier. How does this getting heavier trend reflected by this equation? Well, formula weight. If all of those 5 balloons have the same pressure and the same temperature, then whatever gas has the greatest formula weight, then it would have the greatest density. And xenon, among the 5 noble gases, xenon has the highest formula weight. If you don't believe me, go check the periodic table, and you will realize that indeed xenon has the greatest formula weight. Therefore, xenon has the highest density, and helium has the lowest formula weight among the 5. Therefore, the density of helium is the lowest one. All right, and we are not doing any calculation example here, but we'll do them. We'll try some practice problems in our class. All right.